So you want to see this in more detail and pause it on the specific parts, but it's about displacement, it's about distance, it's about calculating speed, it's about using these equations, knowing distance-time relationships for distance-time graphs and velocity-time graphs, knowing how to use A equals changing V over T. So we're going to use V and U. We also need to be able to use this equation, so v squared minus u squared equals 2as, so we need to be able to rearrange that equation, and it says that we need to know that free fall under gravity is an acceleration of 9.8 meters per second squared. So again, that's the gravitational force, but we should be given that in the exam. We need to understand Newton's laws, so the first law is based on inertia. The second law is based on resultant force being equal to mass times acceleration, so knowing how to use that equation and where it applies. And the third law is for every action there is an equal and opposite reaction. You also need to know about forces and braking distance, stopping distance, reaction times, the factors that affect braking distance, momentum, and the conservation of momentum. Okay, so in the first part of this video, we're going to talk about the difference between displacement and distance. So if we start at this point here, I'm going to draw a line through this maze, and you can see that this is going to represent the distance. So to work this out, I'd have to use a ruler and measure every single part of that line, and that would give me a distance. The reason this is different to displacement is always from the place we start to the place we finish. So if we start at point A and we finish at point B, you can see that the distance and displacement are the same. They are often the same in the exam, but sometimes they are not the same, and if they're not the same, you need to be aware of this situation. You also need to be aware that if we go from A to B and then back to A again, the displacement is 0 because we haven't actually traveled anywhere from start to finish. So it's always the shortest distance from where we start to where we end. And if we end where we start, displacement is 0. Displacement and distance are in meters. Okay, so moving on to speed, velocity, acceleration, and using a more complicated equation. So the first thing we need to know about is the typical walking speed. So you need to be aware that roughly speaking, walking speed is about 4 meters per second. Okay, so something around this, maybe 3 meters per second. Running speed is about 10 meters per second maximum. So Usain Bolt would run at around 10 meters per second. So maybe 8 meters per second for an average sprinter. And maybe this would be between 2 and 4 meters per second, depending on who's walking. The speed of sound, you need to be aware, is 330 meters per second. And the speed of light is 300 million meters per second. So that is 3 times 10 to the power of 8 meters per second. Okay, so let's have a go at some speed and distance equations. So we've got a car. Imagine the car is moving at 20 meters per second. If the car moved at 20 meters per second for 6 seconds, we should be able to use this equation to work out the distance traveled. So if speed is equal to distance divided by time, we can rearrange this equation to work out the distance. We know the speed is 20. If we're dividing by time, the opposite is to times by time, so we're going to do that to both sides, and this will cancel out. So we know that distance is equal to the time times the speed. So the speed is 20 and our time is 6, so that would give us a distance of 120 meters. So be aware of the equation, you need to learn it, and you need to know how to rearrange it. Okay, moving on to velocity. This is a 400 meter track. Okay, so we're going to work out the speed, and we're going to also look at velocity as well. Okay, so if this runner, we talked about running speed, we're going to give him a running speed of 8 meters per second. Okay, so if this runner was traveling at 8 meters per second, we're going to try and work out how long it would take them to get around the track. So what do we know? Well, we know that the speed is 8 meters per second, so we can work out their speed by doing the distance divided by the time. Now we know that the distance traveled is 4 400 meters, but we don't know what the time is because that's what we're trying to work out. Now a quick way of rearranging this equation is that we can just substitute these two. So we know that t is equal to 400 divided by 8. And if we do that, we know that that's equal to 50. And because time is always in seconds, we're going to give that a unit. Okay, so the time it would take would be 50 seconds. Now the reason I used a 400 meter track was just to talk about displacement. Just because the speed is 8 meters per second does not mean the velocity is. He has run this whole lap in 50 seconds, but getting around the track, he's going to have a positive and negative velocity. So when he gets back to the original point, his overall velocity is 0. So whilst he has got a speed of 8 meters per second running around the track, his velocity is equal to 0. Okay, so moving on, we're going to get some more complicated equations. We're going to have a look at acceleration. So I'm just going to remove the ink. Okay, so we've got someone here jumping out of a plane. So imagine they jump out of the plane and accelerate. So they're going to accelerate to 50 meters per second. Okay, if that takes 4 seconds, we need to know what the acceleration would be. So we're going to use acceleration is equal to a change in velocity. Now a change in velocity is given as v minus u divided by t. V is our end velocity. U is the start velocity, and you must remember these things for your exam because you need to apply it with v minus u equals 2as, or v squared minus u squared. So our end velocity, well, is accelerated to 50 meters per second, so that is going to be equal to 50. The start velocity, well, he's just jumped out of a plane, he's not falling, so that must be equal to 0. So 50 minus 0 is 50. We're going to divide that by 4, and this will give us our acceleration. So 50 divided by 4 is going to be equal to 12.5 meters per second, and this is an acceleration, so it's squared. Okay, why is it squared? Because every second his speed has increased by 12.5 meters per second. So his speed has increased by 12.5 meters per second every second. That's why it's squared. Okay, now imagine he's now jumped out of the plane, he's going 50 meters per second, and he's now going to open his parachute. Well, what's going to happen? He's going to decelerate. So for question 2, you might be asked, well, the parachute is going 50 meters per second. He's decelerating, and we'll say he decelerates to a speed of 5 meters per second. And for this question, we'll say it takes 20 seconds to do that. So to go from 50 meters per second deceleration to 5 meters per second takes 20 seconds. So let's use the same equation. This time our end velocity v is 5 because that's what he's ended up at. We're going to subtract the start velocity, which is 50, and we're going to divide that by the time it takes to go from 50 to 5. Now because it's deceleration, it's going to be a negative number, so we're going to leave it as a negative number, and I'll explain why in a second. So 5 minus 50 is going to give us minus 45, and we're going to divide that by the time taken, which is 20. And if we do that, we're going to end up with 2.25 meters per second squared, and that's going to be negative because it's deceleration. Now we've used that, we can now use this equation. So I'm going to use that to have a look at this equation, and we're going to have a go at calculating the distance travelled. So how far would the parachutist go in this equation? Well, we've got this equation that v squared minus u squared is equal to 2as. Well, what do these things mean? Let's make sure we go through them. End velocity squared, start velocity squared, 2 times acceleration times by s, which is our displacement. And because we're trying to find out the distance travelled, that is what we're looking for now. So I'm going to circle that because that's what we're after. So how do we rearrange this? Well, if we're timesing by 2a, the opposite is to divide by 2a, and we're going to do that to both sides. So that's going to get rid of our 2a. So we now have an equation. S is equal to V squared minus U squared divided by 2A. Now we said we're going to use this as a negative number, and that's important, and I'll explain why that is in a second. Okay, so here we have minus 45. Okay, so we're going to use our V squared and our U squared, and we're going to have a look at how long this is going to take. Okay, so we know that the start velocity in this particular case was 50. So we know that V squared is going to be 50 squared, and we're going to take that from 5 squared. So this is our V squared and this is our U squared. We're going to then divide that by the acceleration, which we just worked out. So that is negative, and this is important, and it's 2A. So it's going to be 2 times negative 2.25 meters per second squared. Okay, so let's do this first. So 50 squared, we'll do this down here. 50 squared is equal to 2,500, and 5 squared is equal to 25. Okay, so we now need to look at this equation. So this is the end velocity, so I just need to rearrange this around. Sorry, that should be 5 squared and that should be 50 squared. Okay, so now we're going to look at this equation and we're going to go through it. So we know that 5 squared here was 25, and we're going to subtract 50 squared, which was 2,500. If we do that quickly, we're going to end up with minus 2,475. We're going to divide minus 4.5 from that, and that's 2 times minus 2.25. Okay, this is basically the end of our equation. So by dividing those two numbers, we then end up with our answer, and our answer is 550 meters. So you can see how we can integrate all of this equation and work out the distance traveled from our V squared, U squared, and our acceleration from the previous question. So you need to be able to use these equations and link them together. So make sure you have a bit of practice at this and you know how to rearrange this equation for V, U, and A and S. So here we have two distance time graphs. So here we have a distance time graph and a velocity time graph. On the left hand side we have a distance time graph, which is showing distance on the y-axis and time on the x-axis, and here we have a velocity time graph. Now they are two totally different things, and it's really important that you understand what the gradients, these lines, mean on both graphs. So this first one, we've got points A to B, and between points A and B you can see there has been 20 seconds, and from here to here there has been 40 meters. So using this we can work out the speed. So this gradient, this line here, is going to represent the speed. So how do we do that? Well, remember that the change delta y divided by the change in x will give us the speed. So that is the gradient. This means the gradient. So what is the change in y? Well, that is 0 to 40, so that's 40 meters. Okay, what is the change in x? It's from 0 to 20, so that's 20 seconds. And speed is in meters per second. So 40 divided by 20 will give you 2 meters per second. So from this gradient between A and B, we can work out the speed. If we look at from B to C, you can see that from 20 seconds to 60 seconds, this difference here, there has been no change in distance. So it started at 40 there, and it's still at 40 meters here. So this line here, when it's flat, shows that it is stationary. So the object is stationary here. Here it's moving at a speed, here it's stationary. Now when we get a curve, the curve represents acceleration. So this is acceleration. It's accelerating here, it's going faster here, and then we get to D and E, and again it is stationary. Now this difference here is that it's going back to the original point. So it is still covering a distance in a given time and returning to the original position. So that covers a distance time graph. The next graph shows a velocity time graph. And the line in this particular instance, this gradient, is going to represent the acceleration. So to work that out, we would again do the change in y. So remember, this is our y-axis, and our y-axis is the velocity, and our x-axis is the time. So what is a change in y divided by a change in x? Well, the change in y is the velocity. A change in velocity divided by our change in x, which is time, is equal to our acceleration. So to work out the gradient, that is our acceleration. So let's have a go at doing that. So from here to here, we've got 4 seconds. So I'm going to put that on the bottom of the graph. That is 4 seconds. And what's the change in velocity? Well, we've gone from 0 right up to here, which is 8. So we've got 8 meters per second. 8 divided by 2 is going to give us 2 meters per second squared. So the acceleration of this red line is 2 meters per second squared. Now when we get a steeper line, it means that this is a faster acceleration. So the steepness of the gradient tells you whether it's a fast acceleration or a slower acceleration. If we had a gradient like this, that would be an even slower acceleration. Okay, when the gradient comes back, this is going to be deceleration, or you can see this is going to be a negative value. So you've gone from 8 meters per second here, 8 meters per second here, and it's gone back to 0 meters per second there. So that is a deceleration. The speed has gone from 8 meters to 0 meters per second. Now the only other thing you need to know about on a velocity time graph is what does all this space represent here? Well, this represents the distance traveled. So if you're to work out the distance traveled, you just need to work out the area of the graph, because the velocity times by the time is going to give you the distance. So if you need to know the distance traveled, you work out the area. And when you're doing that, remember that this would be a triangle and that this would be a triangle. So you work out half times a half, plus a half, and then you work out this rectangle. And this will be shown with some of the exam questions later on. Right, this graph is another velocity time graph, but this time it's for showing terminal velocity. So you can see we've got a very steep line here, so you must have a very fast acceleration. At this point here, the acceleration is slowing. So this is showing that there's some other force acting to slow the acceleration down. And here we have no acceleration because it's traveling at 8 meters per second for this line. So that is a constant speed. And when you get a constant speed for an object, it's called the terminal velocity. So if we had a falling ball, you can see that the mass times the gravity is causing it to fall. So the object's mass times gravity is going to give it its weight, okay? Because remember, weight is equal to mass times gravity. So this is the weight pulling the ball down. So the weight due to gravity pulling it down. And when there's only one force, we get a resultant force. Now this is a large resultant force. So the RF stands for resultant force, and this is very large. So let's call this a 50 Newton resultant force. If you have a 50 Newton resultant force and there's nothing pushing up there, then you're going to get a large acceleration. Remember, a resultant force means an acceleration. Now, as it starts to fall, the object, you're going to get some drag. Drag is air resistance in this case. So we're going to have some air resistance caused by the object falling. So the air is going to hit on the ball as it pushes up. Now you can see we've now got this red force. This is the air resistance. So we've still got our 50 newtons pushing down, but the drag force may now be about 35 newtons pushing up. So what's the overall resultant force? Well, it's going to be less. the resultant force, because these are opposite, is going to be equal to 50 minus 35, which is 15 newtons. So what does that mean? It means a smaller resultant force. We can see the resultant force now is 15 rather than 50. So because it's a smaller resultant force, we're going to have a smaller acceleration. Now if we look at this graph, the large resultant force will give us this very quick acceleration, which is this part of the graph. The small resultant force is going to be this part of the graph. It's still accelerating, but it's gone from 7 to 8 and it's taken a much greater time. So the resultant force is small, so the acceleration is small. The resultant force here is large, so the gradient is much steeper. Now in this last part, eventually the drag force is going to be equal to the weight. And when the drag force and weight are equal, the overall resultant force is going to equal 0 newtons, because 50 minus 50 is 0. So when you have a 0 newton resultant force, i.e. no resultant force, the object will travel at a constant speed. There will be no acceleration. And as you can see from this point here, there is no acceleration. So the final part is that, where there's no acceleration, and the object or ball will travel at a constant speed in a straight line forever. Now moving on to stopping distances. Stopping distances are made of two things. The reaction time, which makes up the thinking distance, so that's from this person, say someone's walking out into the road. If the car sees the person, from that person, the time to react from that person seeing the person to the distance travelled in there, so say that's 20 meters. So the distance a vehicle travels from when a person thinks about braking to actually pressing the brakes. So they've seen the person, they're thinking about braking, they've travelled this amount of distance before actually pressing the brakes. Now after that, they're going to press the brakes. So they're going to go a bit further, and say they go 60 meters from pressing the brakes to actually stopping. So that's going to be the braking distance. So the braking distance is when you actually touch the brakes to when the vehicle actually stops. Now both of those combined, our 20 plus our 60, is equal to our overall stopping distance of 80 meters. And these things are going to be affected by different factors. So the first is thinking distance. What are the factors? Well, speed is going to be for both. Drugs and alcohol is going to affect the way your brain works and therefore affect how quickly you react. Tiredness will do the same. And the last one, which I've put last for a reason because I kind of disagree with a little bit, is distractions. So I'd stick in your exam to the first few because they're the most important. So speed, drugs, alcohol, tiredness, and most mark schemes will accept distractions, but I wouldn't put it on your exam. The next one is braking distance factors. Now look, speed is on both, so this factor will affect both. So the speed the car's going will affect both the thinking distance and the braking distance. The other ones are icy wet roads. If the roads are wet, then it's going to take a lot longer for your car to stop, so it will have travelled a greater distance. Low tread on tyres. If it's wet, then you need tread on your tyres, and that will help the car to stop. And the quality of the brake pads. Some cars have very good brake pads, so Ferraris, Porsches, etc. But some cars don't have the same kind of brakes, and therefore the distance the car will travel before stopping will be much further. So it's really quite simple, but just make sure you're aware of at least two factors for each one, and you understand the definitions. The definitions are important. The biggest mistake here is that people talk about the thinking time or the braking time, and it's the distance the car or vehicle travels. Right, for this particular section, I'm going to play a little video.
All right, ready? Little drum roll. I'm gonna count you in. Ready? 3, 2, 1, hard. And the crowd goes.
Okay, so why does the plate stay balanced on the table? Well, this is because of inertia. Newton's first law states objects want to rest and stay at rest. So because the plates and the cups were resting, they wanted to stay resting. So when the person tried to remove the cloth, they wanted to keep doing what they were already doing. This is called inertia. Things like to do what they're already doing. If they're moving, they like to stay moving. and if they're resting, they like to stay at rest. Okay, so here's another animation to demonstrate this. This person here is not moving, so he wants to stay at rest. This obeys Newton's first law. This person here, well, why when the skateboard stops does he keep moving? Because he wants to keep moving. So the skateboard doesn't keep moving because there's no way it can, because of the third law. For every action there's an equal and opposite reaction, so the rock applies the same force back on the skateboard and it stops. But this person doesn't have anything to stop him, so he wants to keep moving at the speed he's going, and therefore he will go straight on. So let's have a look at Newton's laws. The first law states objects keep doing what they are already doing. If they are at rest, they stay at rest. So if an object is going 0 meters per second, it will continue going 0 meters per second. If they are moving, they keep moving in a straight line at constant speed. So if this person is going 10 meters per second, when they hit the rock, he will keep going 10 meters per second, and that's why he crashes. This is the same as car crashes. When you're in a car crash, the seat belt tries to stop you doing what you are already doing because you want to keep moving, and that will put you through the windscreen, which is obviously very dangerous. So that's Newton's first law. All objects want to keep doing what they are already doing. If they're moving, they stay moving. If they're still, they stay still. His second law states that force is equal to mass times acceleration. So you just need to learn this equation and know that the F actually stands for the resultant force. So the resultant force is equal to the mass of an object times its acceleration. And remember, these are proportional. So if you increase one of these, you will increase the force by the same amount. Remember, when we have something like F equals m times a, increasing one of these, such as increasing the acceleration by 10, would increase the force by 10. That is a proportional relationship, and we get those when we get a multiplication like this. Okay, the final law that you need to be aware of is Newton's third law, and Newton's third law states for every action there is an equal and opposite reaction. So this action of the skateboard hitting the rock and putting a force on the rock means that the rock will put a force back on the skateboard. There is no force acting on the person. He will keep doing what he's doing. But the skateboard hits the rock, so the rock hits the skateboard with the same force, and that's what halts its momentum. The last part of this video is on momentum. Now, lots of people find this very difficult, and you just need to use a system for working it out. And the system for working out momentum is that you need to work out the momentum of the whole system. The whole system. So in this first figure, we're going to do the whole system first. So these two people are not moving. So they are going to obey a law of conservation of momentum. Now, what does that mean? It means that the momentum before a collision is always equal to the momentum after a collision in a closed system. Now, what I mean by a closed system is if there is no friction, no air resistance, no other forces acting. So the other forces would obviously stop this from occurring. But when you're doing the maths, you take all of those out of account. So all you need to know is that momentum is conserved for every mathematical equation you will do in your exam. So let's go back to this closed system. Well, before anything happens, these two ice skaters are not moving. So we know if they're not moving, their momentum must be equal to 0. They must have 0 momentum. So if the momentum before is 0, then their momentum after must also be 0. So we can use this momentum after to work out their velocities. Nearly every question you're going to be asked is going to be asking you to work out the velocity of something after the collision. So we know the momentum after the collision. I'll just put after collision AC is equal to 0. So we're going to now break it up into two sections. We're going to do this person first, and then we're going to use their momentum to work out the velocity of the second person. So the momentum of this closed system to start with is 0. So we know that this person's momentum plus this person's momentum must be equal to 0. So let's work out this person's, because we've got a velocity, we can work out their overall momentum. Okay, so momentum P is equal to the mass times the velocity. Well, we know that the green person's mass is 60 kilograms, and we're going to multiply that by her velocity, which is 2 meters per second. That will give us a momentum of 120 kilogram meters per second. Now we know if this person has a momentum of 120 that way, then the other person must have a momentum of minus 120 because they have to equal 0. So 120 minus 120 will equal 0, which is our overall momentum. So we can use this. If we know that the other person is minus 120 and that is equal to her mass times by her velocity, then the mass of the other person is 50 and that's multiplied by v. So let's rearrange this equation. If P is equal to m times v, then v is equal to P divided by m. We know that their momentum is minus 120, and we're going to divide that by the mass, which is 50. So let's make sense of this. Velocity, v, is equal to minus 120 divided by 50, and that's going to give the other person a velocity of minus 2.4 meters per second. So we would know that her velocity would be minus 2.4 meters per second. And to check that you've got it right, we could look at the mass and think, right, well, if they've got a lower mass, when they push against each other, they must have a greater velocity because there's an equal and opposite force. So with an equal and opposite force, the person with the lower mass is going to move at a faster speed. Okay, in this next section, I'm just going to remove this ink. This is called Newton's cradles, and what's happening here is this ball is going to transmit its kinetic energy, and it's going to transmit it from ball 1 to ball 2, and then all the kinetic energy is going to go to 3, and then to 4, and then to 5, and then what is 5 going to do? Because there's no ball to collide with, it's going to then move back to this point here. And if there was no friction, if there was no air resistance, then in a closed system, this ball would go to exactly the same height as the original ball. We know that doesn't happen because there's going to be air resistance, going to be friction up here, so therefore that won't happen. So eventually they will stop moving. But if there was no friction and air resistance, this ball would collide, they'd all collide into each other, they'd transfer their kinetic energy, and this would then gain gravitational energy and it would move back, and they would just keep going backwards and forwards. And this shows the conservation of energy in a closed system, but it also shows the conservation of momentum, because the momentum, the mass and velocity of this object is going to be transferred to all of the balls, and that's going to gain momentum, and then it's going to fall back down again. So the conservation of momentum is kind of like the conservation of energy. In a closed system, momentum and energy will be conserved. Okay? In an open system, energy is still being conserved, but obviously the friction will generate heat, and heat will be transferred to the surroundings. So that is showing both conservation laws quite nicely. Now the last one is another really typical situation where you start off with no momentum. So we've got two cannons down here, and the second one is showing the cannonball flying out. So before the cannonball flies out, the overall momentum of the objects, because they are stationary, is 0. So the whole system is 0, and that is before any collision. So what must it be after? Well, it must be the same because of our rule up here. The momentum before a collision is always equal to the momentum after a collision. So the momentum before is equal to 0, it must be 0 afterwards. So let's now use this to calculate the velocity. So we're going to start off with what we know already. So we're going to say that the cannon recoils at 0.25 meters per second. Now this would be given to you in the question. So what does recoil mean? It means when it fires it, the cannon's going to move back in that direction. So that is recoil. So it's the same with a gun. For the action of moving the cannon one way, the cannon must go the other. And this is another example of Newton's third law. So for every action, there is an equal and opposite reaction. For the cannon to go that way, the cannonball to go that way, the cannon must fire the other way. So if the cannon's going to recoil at 0.25 meters per second, we can now work out the momentum of the cannon. So let's do that. So the momentum of cannon is going to be equal to P equals M times V. It's going to be equal to its mass, which is 1500, and we're going to multiply that by the recoil velocity of 0.25. If we multiply those two things together, we get 375 kilogram meters per second. Now I'm going to, for this particular instance, even though I've worked it out first, I'm going to give this a negative value, and the reason for that is because it's recoil, and I'm going to say going backwards is negative, and that makes it simpler to understand that the cannonball going forwards is going to be a positive. Okay, so we're now going to use this number minus 375, so I'm going to do this down here. Okay, so we know that if this is minus 375 and the momentum before and after the collision is 0, then to conserve momentum, if one is minus 375, the negative here is minus 375, then the positive has to be plus 375, because minus 735 plus 375 is equal to 0, which is our momentum before and after the collision. So we know that the cannonball has a momentum of plus 375. Now we can use our equation P equals M times V again, and we know that the velocity is going to be equal to P, the momentum, divided by M. So 375, and we're going to divide it this time by the mass of the cannonball. So we've got the mass of the cannonball was 5, so 375 divided by 5 is going to give you 75 meters per second. So the cannonball will travel at 75 meters per second if the recoil of the cannon is 0.25 meters per second.